Hi guys, this video is going to be about programming Halo 2 circuits. This is going to be the first of a series of videos that will delve into the programmation of Halo 2. And we're going to start with the basic setup up to more realistic applications. So we're going to talk about how to do some example circuits, and I think we'll see how to do a hash, how to have a circuit that verifies a hash, and maybe some games like Word or Sudoku. All right, so all you need for these videos is some basic knowledge of Rust. And if you want to follow the steps I'm doing here, you can use you can do it with a fairly basic setup, because all I'm going to use is Rust and Visual Studio, an editor, on no, Visual Code as the editor. Visual Code has only one plugin, one extension, the Rust extension. So other than that, there are no libraries or private libraries or anything. Okay, so let's get started. I'm going to switch to the display, and we are moving on from there. Okay, let me see how to do that. All right, this is my display. So, okay, OBS, bye-bye. And so we are, let's launch Visual Code. What's Visual Code? Here. And no project. And cargo new, hello, test, hello example, exercise 1. If we go here, now I need to remove this and add a folder. What's that? No, just hello exercise 1, example 1. Okay. So this stuff is gonna just do hello world. First thing we need is to add the hello 2 crates. So proof and gadgets and proofs. Okay. And that should still do the same thing. Okay, what it compiles? Let's talk about how this stuff works. When you want to create a zero knowledge proof, you're actually not calculating anything. What you want to do is to show that there's a calculation that you have done, and you have done it properly. I think I'm going to run out of charge. Give me a second. Okay. So you're making a calculation, and this calculation involves some secret value, some values that you don't want to disclose. So you are saying that the result that you obtain is a result of a calculation that has involved some inputs that you know about, of course, but that you don't want to reveal. So usually the calculation you're going to make is something that is irreversible. For example, if you calculate a hash value of some secret data, then you're going to reveal the result, the hash, but you don't want to show the secret data. If you're okay with showing the secret data, the whole process is very easy, because you just give that data, and the guy is the verifier calculates the hash and will get the same value. So the whole difficulty here is obviously the fact that you don't want to reveal the secret data, and you want to make sure that whatever you reveal, which is called the proof, is not going to allow the verifier to figure out what the secret value was. So it's just, if you give the secret value +1, it's really not what we want, because the verifier has a clear indication of what the secret value would be. Okay, so that's the context. So when you use this kind of stuff, I mean zero knowledge proofs, you're always going to first do the calculation normally with your secret values, and then implement that same logic in as a zero knowledge proof circuit, and have the proving system make the generate the proof, and then that's the stuff that you give out. The verifier will get the proof. He also has the statement that you want to prove. He also has the same public parameters. In that case, it would be maybe that means he has the result of the calculation, but he doesn't have the secret value. And the proof would give him this assurance that you know that the secret value and that you have carried out the calculation properly. So carrying out the calculation properly is usually easy. The big difficulty is knowing the secret value. So in example that I'm going to use here, I'm going to use the stuff that Vitalik Buterin is the example that Vitalik Buterin usually uses, which is a simple equation that stands for any potential. Could be very complex in practice, but for example, it's a simple equation. This one, x cubed plus x plus 5, and you do that calculation with any value you want first, and then you say that, okay, well, let's do in this example. The calculation he does is with 3. Right? So what we want is to show that if we have 3, so 3 times 3 times 3, actually you can do that in our head, it's really not that hard. That's 27 plus 3, 30, 35. Right? So the result is 35, yeah? And now we want to show that we know a value of x such as the result is equal to 25. So we leave the equation as it stands. This is going to be, this part here is the calculation, and this part here is the public data. So if you replace this with a real case, this would be, for example, the algorithm for calculating a hash value. X would be the input to the hash function, and 35 would be the hash result. Okay. So what we want to do now is a circuit that implements that. So typically, when a circuit, what you want to do is you want to use some pre-made components. A circuit is basically a large matrix of numbers, and so it has rows, it has columns, and it has therefore a bunch of cells, and each cell has an integer, a number in there. The numbers can be added and multiplied, so you can do some basic arithmetic operations, and you are going to define the constraints you want between these cells, so that you cannot plug any value you want. The circuit, the matrix follows a series of steps in its construction, and it's such that for a given algorithm, for a given formula, your circuit is capable of generating or getting the answer, this 35, in a cell, one under the cell. If you put the input x equals 3 in the beginning, so usually at the top of the matrix, and you make a relationship between these cells, simple calculation, and at the end, at the bottom of the matrix, you will have the result. So, for example, what we want is to say that we will start with x, right? And the first row we have. So this is just construction. This is something that you want to do before you begin the design of your circuit. So we begin with x, and then we can put x, repeat x, and there are many ways to do this stuff, right? We don't, of course, it's like programming. You have many ways to program, as long as every row has a constraint that you can keep, that must be kept. Then you should be fine, and we will see what kind of constraint you can have. It's not like you can do a lot of stuff. Everything is fairly basic, but it's all these series of basic operations that at the end can build something very complex. So I'm thinking of doing x, so multiplication, and then okay, so that's kind of hard to see already. So something like that, and the dots are essentially values I don't know what to put there, and they may mean no too many columns or not enough. So we are kind of designing it as we go. So we have x squared. If you multiply, so what you want to do is break it down to fairly basic steps that can be done with arithmetic operations. So what I'm saying is that if we do just multiplication and addition, so one step at a time, either one multiplication or one addition between two cells, then we eventually going to get there, right? So if you continue multiplication, so what I'm saying is if we start with something like this, and then the second row is that, or we could actually start with, okay, let's continue like this, and maybe we optimize later. So that's pretty the simple way. And then this row would be x cubed plus x. I'm leaving a little bit of space. All right, what I'm saying here is that we multiply these two guys to get this value here. And then we multiply these two guys to get the value here. Oh, this guy should be moved forward. It's like really like this. Then we multiply these two guys to get the next row. Then this one is an addition, and this one is another addition. Right, and then we would have the final result R here. And we have to constrain this value R to be equal to our predict data. Okay, so if we start by putting x and x instead of just x, then we don't need the first row. So essentially, the idea is that you can put the secret data anywhere you want, and you can constrain two cells to be equal. And you can make any calculation between cells as long as you say that the result has to maintain a particular constraint in a region of the grid. So and the constraint that we're going to put is that these for any given row, like this one or this one, column 0 and column 1 either multiply or added will give the next row first column. All right, so if I'm here and I see I want a multiplication, then I get this one. So obviously we also need a way to tell apart rows that are added and rows that are multiplied. So I'm gonna have a flag here that says it's a multiplication. So here is apply, here is apply, and here is added, and here is added. Oh, sorry, what am I doing? So it's not multiply, and this one is added, and this one is added. And this one is not added, this one is not added. And we actually don't need these columns then. So I can remove this, and we have our circuit. So this is our circuit. Has 5 rows, and the last row, we don't really care about the values. So it could be anything they want, and this will not be constrained. So the only constraint we have at the end is that R should be equal to 35. All right, so now we have a design. Let's go about implementing this logic. So when you implement the logic, you have established the constraint that you are going to use in your particular region. So every region here is going to follow. In this very simple example, there's only one type of region of constraint, but in a real case, you're going to have multiple ones, because it's not like you can have the constraint you can put are rather basic. You can only have polynomial constraints. So if your program has more complex logic, you're going to have to enforce a particular constraint on certain rows and completely different ones on different rows. If here we only have 2, in the real program, you're going to have like many, like 10, 12, 20 different types of or maybe not that many, but a lot of different kinds of constraints. And if you had them all in the same location, it would become very hard to maintain. The code would be very difficult. So it would be like having one main function and put everything in there. Technically, you could write very, very complex programs with only one function, it would remain. But obviously, it would be really hard to read. So what we have instead is the concept of chips. So we have a circuit. So circuit is this guy here, right? So that's what we want to lay in memory at the end. So we only have one circuit for one type of zero knowledge. Then the circuit though can use multiple chips, and the chip is some kind. It's like a function. You have a certain logic. For example, you have a chip to do hash calculations. You would have a different chip than to do elliptical curve calculation, and so on and so forth. Right. So each chip would have its own logic, and usually the chips themselves, they would even do something that is too basic to qualify as you still want to group this stuff together, right? So a chip would be for example, like a class, but your function could use more than one chip. So higher than that, you have the notion of a gadget. It's something that combines the usage of multiple chips. So for example, if you have the calculation of the calculation of the nullifier in Zcash, if you're of a commitment, or Merkle tree, like the Merkle tree, the calculation of the root of Merkle tree will involve hashing values across different layers. So you are going to use multiple chips for that, and that would be a gadget. So in our case, we're not to need the gadget at this point, not yet. We need to, well, we don't need to, but we're going to use a chip so that we are going to not to repeat the same code over and over. So we can see that the code here to multiply the stuff is going to be used 2 times, one time to get x squared and one time to get x cubed. And the logic to add an addition is going to be done with plus x, and another time was plus 5. So we have we use addition 2 times and we use multiplication 2 times. So that works. That's worth making a chip for that. So let's go. Our chip has a configuration. So we're gonna call this chip the arithmetic chip. So arith chip, and it has a config. So I'm gonna call this guy arith config, and then the arith chip. The config is where you have the definition of your column types, and the chip itself is where you have the code that will implement the logic for these operations. So we can expect the chip to have a function for adding, and then a function for multiplication. So just do it like this. No, okay, of course it's not there. What kind of Rust is this? It's in implementation. And the chip itself contains the config. So config will be here. And the chip has a function to configure it, to get the config. All right, so I'm just giving the skeleton, and it has the parameters are not there, but it's just to show the typical functions that you would have. It's not really an interface, but this is a standard that I've seen used by most people. And then you have a construct that takes the config and returns the chip. So let's say it takes the config and then returns the chip. Returns the chip which itself. And this is also to do. Okay. Then we are saying that arith should implement the chip interface, the chip trait. And we have to decide which type is going to be in the cell of our circuit. And for the case of in the case of Zcash and Hello2, you can choose whatever you want as a field value, and especially for this one because the values are really small. But what you want to do in practice is to make it align with the type of calculations you're making, because all the calculations you're going to make on the cells are going to be modulo the field. Or it's going to be like values of that particular type. So if, for example, you want to do elliptical curve calculation, what you really want is to have that type be the same as the type of your base field, so that you can do the addition and multiplication very, very easily, because it will automatically be done in the same field. But in this case, it doesn't really matter. So I'm going to just use the same as the one from Zcash, and that's FP, the one that's Palace. Or FP implement FP for Arith chip. Okay, so now it's going to start yelling at me because it doesn't know about this stuff. How to import, and how to implement. Okay, now config, that's pretty logic. It's going to be this guy. We need clone. So we have to derive clone. Nothing special about this guy. And debug. This one is kind of like the setup, but there's nothing special about this guy, so it's going to be unit. And these guys are just accessors. So self-config and loaded, we return nothing really. Okay, so that's it. As you can see, it's strictly very simple. We have also some implementation for config. So we need, but config has no interface. Okay, so what's going to happen here is that we are going to get our circuit, and then we are going to, the framework is going to give us an object that we need to define the column types. So to help me with that, I'm going to also put some placeholder skeleton code for the circuit. So it's a Vitalik circuit since we are implementing the Vitalik example. And it comes with also config, struct Vitalik config. And the same story goes here. We need that guy to implement the circuit logic, the circuit trait. Implement circuit for Vitalik circuit. And this is going to be imported, and it's going to be implemented. And it follows the same pattern. The config is tied to the circuit, and again we don't have clone. So derive clone, and the floor planner is the stuff that's going to set up our circuit based on the rules that we're establishing. So there are several of them. I think for us, the simple floor planner is enough. With our witness is should return an empty circuit. So we want to return the default, which means that this guy here has to derive default. Okay, so we have that, and then we have these two guys that are, these are the stuff that we need to use to set up our table here. All right, so synthesize is configure is where we set up the establish the metadata, the column metadata, and synthesize is where we actually write this code here. All right, so configure is fairly easy because all you need to do here is define your columns, as I said, and we have two columns where we put our values. So these are called advice columns. We have two columns where we select the operation to do. These are called selectors. And we have one column, which is, I didn't put it here, but we have one column to put our public data, because somewhere we need to have this 35 here, right? So this, you need a column for that. And then at the end, it would be that this R is constrained to be equal to this value here. So let's do that. We have advice column. We call it A. Okay, let's label columns. We have column A, column B, column selector multiplication, and you say sector addition, and we have let's say P for public. Right, so let's put some space. All right, so two columns of type advice, so this is one, and this is the second one. Column A, column B. We also said we want selector A for addition. Yeah, selector M for multiplication first, though the order doesn't really matter. This is called selector. And then we have another column for the addition. Okay, and then we have one column P for the instance, meta instance column. Okay, and actually we have one more here because we have to put this 5, and 5 is a fixed value, so we need one column, or at least define a column for a fixed value. If we don't, the framework will yell at us. So if you forget about this, it's actually quite easy to know. We're going to leave it out and see what the framework is going to tell me. Okay, so these are the ones that are obvious. And then what I'm going to do is I want my config here, Vitalik config, to hold one of the chips, right? So one instance of this guy. So it has to be that the Vitalik config contains the arith, well, actually just chip, but just arith config. And that's that. And then I have to configure that guy, right? So to configure that guy, I do a call configure on the so this the chip ith. What's the name I use? Chip config. Let's call it chip config. Okay, so I have chip config be the result of this guy with chip configure, right? And what do I need to pass? Well, I need to pass everything basically. I need to pass A, B, SM, SA, and P I don't, because P will be, the chip is not going to do the matching with P. The matching with P is done in a circuit. The chip is going to do the operation A plus B, A times B based on SM or SA. So these are the information, the columns I have to pass to it, so that it knows where to do the calculation. So it's going to be SAB, and also I need to pass the meta. So that gives me the signature that I want for the configure. So I need to copy that type here into configure, and then say that we also have A as column advice. Again, advice columns are the ones that contain secret values or result of calculating stuff on secret values, and SM is a selector. So this is what the columns you use to determine what kind of operation you are doing. Okay. And there are some, oh, he doesn't know what the column is. So import. What do I mean? Yeah, this is wrong. The column here is not that type. This is a column in Plonk. And advice is also in Plonk. Okay. Then so far so good. No errors. A lot of warnings though. And configure. Okay, we'll have to do the configure. So this configure, I'm gonna say that I need to be able to do equality on these columns. So I have to say that enable equality on A, same for B, for everything actually. So B, well, selectors no, right? And then I have to define the gate, right? So I have to define the constraint that I want to have for this chip. And that's done by doing a create gate. So this is probably the most important thing that the chip has in the configure section. That's going to be the arithmetic constraint. Then you get the metadata. Here you're supposed to, you can recover the values of A. So actually here you're binding, you want to, okay, so what we want to do here is to say that on the given row, if we have A, B, SM and SA on the row 0, the next row will be either will be the result of the calculation, so AB or A plus B. Here we don't know, well, it's going to be the next guy, so we don't know. But we want that guy here, or let's call it R, to be R should be A times B if SM, and R should be A plus B if SA, right? So that's the logic. Put that as a comment. Would be nice to have. Okay, and then we implement the logic. So let A equal a meta query advice on column A at the current row. So that's called rotation current. The terminology is a bit strange, but you can use to that. And then B would be, well, the same, but would be. All right, and the result is A. Sorry, is A at the next row. So then rotation next, and then we are saying that we want to constrain this one, the first one. So R minus AB should be equal to 0. So all the constraints are basically going to say that some calculation is equal to 0. So we want that if SM is set. So we do SM multiplied by this. And we know that SM is either 1 or 0. That's part of the framework. So if SM is 1, then R must be equal to AB. And so that's our first constraint. And so we are supposed to return a list of these guys. The second one is R minus A plus B. And this should be true if SA is 1. So we set also the same trick where we multiply by SA. So something is wrong here. No, sounds good. Then that's that. Okay, and what's going on here? Oh, okay. So this is an error because I do a question mark, and this function returns a config. So actually, this is not the type of create gate. Create gate is not returning a result. It's returning nothing really. All right. So okay, like this, and that's it. This is our. Oh no, I have to return the config, right? So we have to make config that essentially has everything. We have A, B, and SM and SA. So this should be put into the config. A is a column advice. So as you can see, it kind of flows logically. If you start finding the stuff, it's a lot of mechanical stuff, meaning that a lot of code that seems to be placeholder. So I hope that one day there will be a compiler for this, so you don't have to write all this stuff by hand. But at the moment, this is all we have. SA, we also have SM, which is a selector, and SA, which is a selector. Okay, so we still have some errors. What are the errors? Oh, this one here, column A. Okay, so this is just a Rust thing. If you have A, you cannot use A again because it has been moved. Right, so I have to clone this guy. Okay, and then there's still errors. Oh no, that's not because of that. It's a type problem, right? Oh yeah, that's because when I do let A equals this, A now is the expression. This A here has hidden the column A. So what can I do here? I just need a different name really. I could call this column A, column B, CA, CB. And now I have to do CA, CB here. And then CA, CB, CA. And then it should be happy. Okay, that's happy for this part. Here is SM times, what's the problem? Oh, AB doesn't exist. It's E times B. Are you serious? And SM, oh, SM I didn't ask, right? I didn't get. SM is a meta query selector of SM. And same thing for SA. Okay. All right, so what else? Only one left. AB, SM, SA. Oh no, it's not AB, it's column A, column B. Well, still problems. Expression A. Oh, here is a here. This is really what is need a clone. Clone. Once you use an expression, you cannot use it again because the expression has consumed it. It's a Rust thing. All right, so no more errors. And we have our chip configuration. Now we want to construct a chip based on configuration. This stuff is essentially creating this chip once we have the configuration. So you want to do this, and you pass the config. Nothing special about that. And now I'll add and multiplication. This is where the logic is really coming. So what you're going to get is this guy here, the layouter, because you're going to call it in this synthesizer, right? So you're going to pass this dude. This guy is going to come, well, you want to have this one, and you want to have the two values, the two cells that you're adding together. So that's the type is assigned cell, FP. And the second cell is B, and it's also a cell. So assigned cell is a cell that has a value, and what you're going to return is a cell. So you're going to return. What am I doing here? Yeah, assigned cell, and yeah, and although an error. And this is also to do though. Error. Okay, error doesn't know what it is. An error should be the Planck error. Okay. So obviously we don't have anything, so I'll put to do. And here we use layout. Indentation is weird, so let me indent properly. Layouter. And the layouter is going to we're going to assign a region of the circuit of the grid for this particular calculation. So we get a function that just tells us the name of what we want to do for this region. So it's going to be add. We can put whatever we want here, and now we really have to do the region. So something like this. And here is the logic for this particular cell. All right. So what we do a addition is we want to activate the gate, the selector for addition. So to do that, this guy is a method. It should have self. We grab the config. Okay, we grab the config, and inside the config we have this selector, and we have to enable. So we enable on this current region at offset 0. Offset is the row, so on the current row, and that's one. Then we grab the actual values. So we have to read the values and make it assign it to these columns. All right, so that's what it's gonna be. Let A equal region, and we assign advice on it. So this is gonna be a loading A. On which column? Column. What's the column here? Self.config.a and offset 0. So this is basically saying that the on the columns A of row 0, you want that to be the value that you have assigning from. Right? So you are reading this value here, and that's A dot value. Let's put the to do so it doesn't yell us. Okay, anything wrong so far? There's this guy, question mark equal, and there's error somewhere. Okay, this is not A, this is A dot value. So we put the value here. And this guy is, okay, we have to copy the value. Copy the. Now this is weird. If you do this, this is not what you want, because that's gonna just copy the value. It's not gonna bind the value to be equal to this guy as a constraint. So that's not right. What you do is you want to copy the advice, and then on A, and on this. So this is gonna copy the value and also make it equal. The column is that we got correct. This is A, and the offset is really 0. Current row. And layouter should be immutable. Okay, so we're back to good. Then we do the same for B, but this time B is on the second column, on column B. And now we do the addition. So the addition will be the result is A dot value, and we zip it with B dot value, and then we have in this callback we have a tuple A and B. This is the standard way to do to unwrap because the value is basically an option. When you are doing there are two passes. When it does the proof generation, it will go through the path where it has the values because it has the secret data, but in the phase where you're verifying, the A and B would not have any value. So to make that code not explode when we have no value, we are doing this map thing where it's basically the same thing as an option type. If the type or the value of A is known, then this raw result will be known. The calculation will not be done. So this is it. It looks weird, but yeah, that's the way it is. Okay, A plus B, and that guy we assign, because we just cannot put it inside the cell, because we know that the constraint will be coming from this guy here. We have activated the gate SA, the selector SA, and this is our current gate. So this constraint here will be active, and we'll make sure that R, A, and B are following that particular relationship. All right, so I'm gonna say region assign advice, because this is a calculation, and this is A plus B. I'm putting it in column A, but at offset 1 because it's one row below, and then this is could be R. Okay, and that's it, right? That's all we have to do. So I'm returning OK if everything went well. And the result of assigning this, I want to be actually this value here, a n plus b. So I'm removing this OK, and I want to return that guy here. Okay, so that should give me R as the assigned cell, because this is the last expression. And therefore, I don't actually need to do this. I'm just going to return R. And therefore, I remove that guy here. We nicely fall through and return the last expression. Okay, so this is add. And obviously, multiplication is going to be very similar. So I'm just going to copy paste multiplication. For multiplication, we have essentially the same thing, except for the calculation, it's going to be multiply. Right, so here's going to be, the comment would be multiply, and here we're multiplying. And the fact that we're activating the other gate, we're activating the SM gate. And that's it. Still 0 errors. That means that our code is correct here. Any other to do must be, configure. Configure, what did I do? I have the arith config, but also want to save the column P. So this guy here should also have the column P for column instance. Okay, so now we can complete this code here by saying this is a Vitalik config with the chip config and P. Okay, so we have only one to do, right? No, yeah, one to do. Okay, so now we're gonna, in the main circuit, we're gonna call these guys. All right, okay, let's leave the to do. All right, what we do is first we create a chip. So we have our arith chip. And to do that, we call arith chip construct, right? From the config we are being passed dot chip config. Probably different name should be better, but it's good enough. All right, now that we have that, we also need to load the values to our first row. So somewhere this circuit must have the value, the secret value. So I put it here, value of FP. This is the secret. It doesn't know what the value is. Okay. All right. So let's go. Layouter dot assign region. So you can see the same code really as in the chip. It's just that we factored out the common parts where we add and multiply into a chip. So this is loading X. And the assignment will be multiple region. On this region, we are assigning advice. This is the X, this X here, the first X. Right? We want to put this guy here. We want to put this guy here. Okay. The X. Our column is config dot chip config dot A offset 0. I'm going to assign it to self.x. Happy about this to do. And we do the same actually with the second one. It's still X, but it's in column B. Right? And then, okay, X is 0. Maybe it helps. X 1. Then what? Then this returns, well, we should return the 2 columns, right? Because we want to use that to call, right? The next one will be using our chip to do multiplication. And you remember the first parameter is a layouter. So something like this will work. X times x, and then we have to pass these cells here, this one and this one. So we need to return these two values here, even though they are the same values. They are bound to different cells. Let's call it at x1, and this one is x2, and then we return OK of x1, x2. So that means that this guy here is x1, x2, right? And then we can pass it as x1, x2. So this way we loaded the cell on x and x, and now we are passing it to the function multiplication that is going to use these values to calculate x squared. And what else do we need here? That's it. And the result is x squared. Right? Layouter has to be mutable. Then what do we do? Well, we could put another x here, but what I'm going to do is actually say that it's the same as the one that we have before, right? So x squared. Pretty well naming here. Yeah, it's confusing. Let's call it x squared. I copy pasted this stuff. So this is going to be x cubed, and x cubed is x squared, and I'm going to bind to the same cell, x1 or x2, same, x1. Then this is these two guys here. We have here. Now we did this one. We did this one. Now again, but this time is x cubed plus x, and we are using the addition this time, and again with the same x cubed. And finally we want to add 5. So to add 5 we have to load the fixed column. So we do let f equal, this is where I was wondering how to load the fixed column, right? So let's see, we can do region dot it's layouter. There's no region here. Layouter dot assign region is, we call it 5, and the assignment will be what to do with a region. Now, what I want to do with a region is to simply assign advice from constant, and here the constant is 5. The column is config dot what? Chip config dot a offset 0. This is a new region. It's not going to conflict with the other guy. And the constant is 5, so it's going to be fp from 5. Okay, there's an error. No, we are returning this guy. And then this is like that. Okay. So now our result is I'm using the chip, chip, and to do the final addition between layouter namespace. This namespace stuff is so that you can have nicer debugging if there's a constraint, something error in your circuit. It's not going to show up as you are running this code, because all of these are callbacks from the framework, the layouter. The layouter is going to be responsible for putting these assigning regions and calling this code to assign the cells. So you can see that all these are closures. They are function callbacks that are actually driven by the Halo 2 framework. So to debug this stuff, you can really not debug the code here because this is not where it's going to be called. This namespace helps you have a better message. So it's just a result. In practice, you probably should have much better messages than what I'm being using. So what I add is x cube plus x, and then the 5. And the result is r. Okay. And finally, I want to say that the there's a constraint between r.cell. This is the contents of r on the current to the column p. That could be self.p. It should be the same because otherwise we either did the calculation improperly or we don't have the proper secret value. So that's the final constraint. And this is okay. All right, so there are errors. Cube is x cube. Another error. How to see this? Okay, so there's an error here. Okay, instance he doesn't know what it is. Yeah, there's still one error here. Actually, you cannot see the zigzag. Oh, here, P. P, is that P? It's self.config.p. No? Oh, it's config.p. This is... Oh, still an error. Mutable region. This stuff has moved. What has moved? Oh, okay, config.chipconfig is gone because it went to this guy. So I can clone this. That would be easiest. And x1 here. Okay, I can clone this one too. Okay, the way we do clone is you have to do clone before, and the last one is the one that has no clone. Because you clone so that you don't have to move, and then the last one is the move. Okay, so this is working. Just one warning here. This guy is not needed. All right, so we have we finished. Took a long time, but we finished, and we want to try it. So to try it, we're gonna use the mock prover, which is development tool or development stage for testing circuit. The first parameter is the size of the circuit. So you try 4 should be enough for this such a small thing. The circuit you have to pass. So circuit would be Vitalik circuit, for which we know that x is a value that is known to be equal to 3. Then we have to pass this. Like this in the to do. Okay, and then the instance. And instance is a vector of vectors. We have only one instance here, so it's going to be a vector of only one value, and this value is 35. Okay. And the result of this is something is wrong here. The result of this is the prover, or result of prover. Or this guy has to also return a result. So result of nothing, an error. So we have the prover, and the prover can do the verification, verify. And then that should also succeed, so we can unwrap. If this fails because the circuit is wrong, or because the witness is wrong, we don't have the right value of x, then this guy will also not unwrap, would panic. And that's it, so we can run. All right, it says not enough columns for constant. So that's the part I was afraid of. Well, not afraid of, but I think that probably we would run into a problem. The problem is that when we do this fixed value, the 5, we actually need to have some column to do that. So we need a place somewhere we say meta instance, not instance, fixed column. We really don't have to store it, so maybe I just can just put it like that. But we need to have one. Sorry, it's here. Then we run again. Oh, it's not to do actually. It's okay, right? And then run. Not enough columns for constants. And that's still weird. Not enough columns for constants. Need more than one? That's very surprising. Okay, it's not because of that. Meta advice. Meta selector, meta fixed column. Oh, sorry. When we create the fixed column, we also have to say that it's a fixed column. We have to say enable constant on column F. So I'm actually gonna put this in the main code. Yeah, no, it should be quite clear here. Yeah, it should be here because it's not something that the chip should know about. It's the fact that in our formula we need one cell that has a fixed value. So then we have to define one column to hold a constant value. There's no room in this circuit for that. So hopefully this was it. Let's run again. All right, so that's another error. Column not in permutation. All right, is that 3? Okay, so I think here is the fact that what is the problem? Index 0, column type instance. Okay. What's going on here? Well, we have created our, okay. So we have created our advice columns and then our instance columns, and the advice columns, I set the equality constraint on it. I've said that somewhere. I said enable equality for CA and CB, which are the first two columns, but I didn't say that should be also enabled for the instance column. So here we have to put enable equality for P. The messages are a bit it's difficult to interpret. I think the clue is the type is instance. Yeah, so next time it worked. All right, so this time it worked, and run it from the command line. Yeah, 35. And if I change the value here, in say it's where is it? Here. It's I don't have the right witness. It's a try with 4. Then I expect it to blow up. All right, so I have error here. This proof doesn't work. And if I have the right value here, but not the right value on the final result, so this also should blow up. Well, it blows up as well. Of course, this doesn't really prove much, except that our circuit is built properly, and we have the right witness and instance. Okay. After that, we can also change this to actually create the right binary proof. but that's not super interesting. It's rather mechanical. The difference is that instead of using the mock prover, you're going to use a real prover, and you're going to use API to create the proof, and then it would output some binary data. Then you take that binary data and you use another API to verify it based on the same circuit and the same instance. Basically, this mock prover that does both of them at the same time. It also adds some debugging information. So obviously, in production, you want to use the real stuff. But yeah, maybe we'll do that later. All right, so that was our first circuit. It's pretty tedious. Well, it's not super tedious, but it's not super simple. And but the stuff behind it, the math behind it, is very impressive, in my opinion. And actually, the capacity is quite impressive, because doing this, being able to program and have any kind of a statement turn into a proof, and rather, I don't know how long it is, but it fits into constant 4. I think even constant 3 should work. Constant 3 is very small though. Yeah, it's not enough. 3 means probably like 8 rows, right? 4 is 16 rows. It's pretty cool. And the next time, what should we do? We already did circuit and chip. So I guess this next time we're gonna try to do with a gadget. So moving one up, we're gonna use a gadget, and to make it more realistic, more practical, instead of having this formula x cubed plus x plus 5, we're gonna do a real application using a hash function. So we're gonna say that we're gonna program a circuit that verifies that a value of x, such as the hash value of x is equal to h, and h is the parameter. So now h, instead of being a function that does this, is going to be a hash value, and the cryptographic safe hash value. So something that really, if you don't have the value of x, nobody will be able to reverse the stuff. So stay put for the next video, and I will try to do it as soon as possible. May take a few days for this video to be processed and uploaded. Until then, if you have questions, please ask, and have a nice day.